Okay, now let's get started. So it is my great pleasure to introduce our speaker today, Dr. Junjae Lee, for webinar. Junjae earned his PhD in chemical physics from Indiana University, Bloomington in 2015. His doctoral research centered on developing ab initio quantum nuclear dynamics methods to investigate quantum nuclear effects in chemical and biological systems. After his PhD, he pursued a career in high-performance computing driven by a passion for advanced scientific computing. From 2016 to 2020, he served as a HPC principal analyst at Indiana University System. Since 2020, he has been a research associate at the Texas Advanced Computing Center, also known as TAC, which is in the University of Texas at Austin. At TAC, his research focuses on performance studies, particularly on the emergent architectures. He develops innovative HPC performance benchmarks, novel profiling tools, and other performance analysis tools to optimize the efficiency of scientific applications. So let's welcome Dr. Junjae Lee.
Thanks, Yang. It's a great pleasure to be here and discuss some of my recent work with you guys. I talked about this tool several times in computer science conference, but really this tool is designed for scientists, designed to help people who run the code, who develop the scientific code to better use GPU. So it's exciting, and I'm glad finally I get a chance to deliver this work to the real target audience I intended. So a little bit more about me. Yang covered most of my background. I just want to show you what a nuclear dynamics looks like, because it looks weird and a little crazy. So the movie here shows the nuclear dynamics of a proton. So that's not electronic wave density. That's nuclear wave density. And you can clearly see this is real-time simulation, not the imaginary time in PIMD. And as time evolves, you see the nuclear state shuffles between different excited states. You can clearly identify first and second excited states. So it's just super cool. And we saw the nuclear Schrödinger equation on a grid. So I can call this real space nuclear electronic structure, nuclear structure. And it's an interesting connection to what I'm going to discuss today, because the code that brought me into doing the automatic offload was a real space electronic structure code. And that code uses very similar method to what I did for the nuclear. All right, so a quick outline of our discussion today, because I know not everybody follows the latest development of computer architecture. So I'm going to do a really quick review of the GPU architecture, including conventional architecture and the newly came out Grace Hopper architecture that has unified memory capability. Then I'm going to talk about the design philosophy of automatic offload, BLAS offload the library. The library is designed to be used by two codes so far. The first one is the parsec of the real space electronic structure code, and second one is the master doing linear scaling DFT. Okay, so GPUs. Conventionally, we're going to have such a GPU architecture. The CPUs and GPUs are separate, and they have a disjoint page table, meaning that the CPU and GPUs all manages their own memory space. And the CPU cannot access GPU memory directly, and GPU cannot directly access CPU or the main memory directly either. So no direct access across each other's data. And data on the main memory, when needed to be used by the GPU, you have to make a CUDA-MEM copy, copy the CPU through some connections, enrich it to the GPU. After you're doing the calculation, you have to copy the data back to your CPU. And GPU memory can only be allocated by CUDA-malloc. And that's how GPU works conventionally. And just last year, there came out a new architecture from NVIDIA called Grace Hopper. So Grace is the name of the CPU, and Hopper is the name or code name of the GPU, and this architecture is also referred as the GH200 internally for NVIDIA. This architecture is very unique, and instead of having separate CPU and GPUs, these two chips are tightly integrated in a superchip. And these two chips are connected by a newly designed NVLink called a chip-to-chip or C2C NVLink that runs at 450 gigabytes per second per direction. To put this into perspective, the most common GPU interface that you're going to see on servers is going to be the PCIe Gen 5 16 lanes, and that can only deliver 64 gigabytes per second. So the chip-to-chip NVLink is going to be 7x faster than the conventional PCIe bus. And this architecture, of course, supports the conventional GPU memory management. So whatever works on the older GPUs also works on the Grasshopper. But more importantly, this architecture supports unified memory management because the chip-to-chip NVLink supports cache coherency. And this is very important. Cache coherency is very important when you have multiple chips in the same memory space, just like you have dual socket CPU in a conventional CPU nodes. And the Grasshopper nodes are available at TAC on our latest supercomputer called Vista. So you can apply and access through either Exceed or whatever the NSF allocation system is and get free access. All you have to do is write a proposal. So a little bit more about the unified memory. When operating in unified memory mode, Grasshopper is going to have a single page table covering both the CPU memory, which is the LPDDR5, and the GPU memory, the high bandwidth or HBM3, all in a single memory pool. So both the CPU and GPU can access all of this memory through unified memory access. As I said, cache coherency is critical for unified memory. For people who don't know what cache coherency is, it basically means the data consistency when you have data shared by multiple processors. And this is common in a modern computer architecture. Even on a multi-core CPU, each CPU has its own L1 and L2 cache. So if you two cores are trying to access the same piece of data, the data is going to store the caches of both processors. And one processor trying to modify that piece of data, the other processor needs to know and get updated. And so they see the same data or consistent data. That's what a cache coherency is. And all systems with multiple chips needs to have that capability instead of have real unified memory access. NVIDIA used to have another thing labeled as unified memory back in 2016. That thing is now called CUDA managed memory. And that's very different from the unified memory we're talking about here today. Because in CUDA managed memory works for every GPU, even the PCIe cards. But it's sort of a software simulated unified memory. It relies, you do have a single page table, but you cannot have direct access. The access relies on the page fault mechanism. And once you do a cross-socket access and the GPU sees the page fault, it can move the page over. And that's very expensive because oftentimes you're going to see very frequent page movement. Even you do a 1 byte access, and a whole new page needs to be moved. And memory on Grasshopper can be allocated in many different ways. The table in the bottom shows you the behavior of different memory allocators. You can have the conventional malloc, just like you do for every C code, and also CUDA malloc manage. And both of these allocations are going to be unified and can be coherently accessed by both processors. While if you do just a CUDA malloc, that piece of data belongs to the GPU, cannot be accessed by CPU, and CUDA malloc host is going to give you a CPU-only data. So after architecture, I'm going to show you the performance capability of the GH200. Here are two industry standard benchmarks. On the left is stream benchmark. Stream is a benchmark that measures sustained memory bandwidth. And many of the HPC codes, including MAS, has some level of memory bandwidth dependency. So you see, when CPU trying to access the LPDDR5 or its main memory, you can reach 418 gigabytes per second memory bandwidth. That's a really good bandwidth for the CPU. And when GPU trying to access that LPDDR5X, it can reach 610 gigabytes per second. And when GPU trying to access, you can make notes here, if the GPU trying to access the HBM or its own memory, it can reach 3.7 teraflops per second. So that's just an astonishing bandwidth and ensures the GPU performs appropriately. However, when a CPU trying to access the GPU memory, all you get is 142 gigabytes per second. And what that means is even though the NVIDIA employee, CUDA people may tell you that on Grace Hopper unified memory, data movement doesn't matter, and you don't have to care about data movement, but data locality still matters a lot. You do have to worry about all of those if you care about performance. And we're going to see how much data movement costs later on when we do when I show you the test numbers for real applications. On the right, we have the HPL benchmark number. HPL is a popular benchmark that gauges the double precision floating point capability of a processor. When we use cuBLAS, they can use the GPU tensor core. And the numbers here are just giving a big incentive to port your code to GPU if your code runs a lot of double precision calculations. So a single CPU can only give you 2.8 teraflops, whereas a single GPU, the Hopper GPU, can give you almost 53 teraflops per second, so almost 20x. So GPUs are really, really capable of doing double precision operations. All right, so we all have a chemistry or physics background, so we all know what BLAS is and how important BLAS is to our life. It is really the fundamental building block of many scientific applications. And it is the basis for other advanced linear algebra libraries, such as the LAPACK and the ScalaPack. And linear algebra is really the natural language of quantum mechanics. So many quantum chemistry or quantum physics code heavily depends on FP64 BLAS performance. And as I said, the GPUs are super capable of doing such calculations. So the quantum chemistry and physics application could potentially very well fit for GPUs. Just that the codes are too complex. Some codes are legacy codes, and it's very hard to port them to GPU. So my journey with auto offload started when I worked with the Parsec people. It's one of the important code at TAC, so I worked with that team. It is a real space DFG code developed at UT Austin by Professor Chudikowsky, and Parsec heavily relies on DGEMM operations and have a profile in the bottom showing you that the total runtime is 681 seconds, but you run your DGEMM 524 seconds, so 77% in BLAS and 77% almost all in DGEMM. And most of the DGEMM calls come from ScalaPack. So PDGEMM and PDTRSM, this code has never been run on a GPU before. And Professor was super upset because not be able to run it on GPU means he cannot run his code or apply for machine hours on a DOE machine, because the DOE machines are all GPU centric. And not only DOE, even attack, we're becoming more our machines are becoming more GPU centric. So it's very problematic that this code is not able to run on GPU. So I was thinking, can I replace the BLAS to cuBLAS, because the code spends so much time on BLAS. But there's no way I can rewrite scale pack. Almost all the BLAS calls in the code are from scale pack, and rewriting scale pack is a hell lot of effort. And replacing CPU BLAS with cuBLAS is also a bit of trouble because cuBLAS has slightly different interface than the CPU BLAS. And also I have no intent to rewrite user code unless I really have to, because we serve a lot of users. Can we do something automatic for users and not only help parsec, but also have a broader range of applications? And at the time, I was developing a new profiler, so I mastered the skill of doing symbol interception. So I was thinking, can I do symbol interception, replace the CPU BLAS call with a BLAS wrapper, and do automatic offload? It turns out automatic offload is not new. It has been around for over 10 years, just never been useful. Started from the Titan at Oak Ridge, that was 2008 or 7. Cray libsci library offered that capability. And later on, IBM ESSL and NVIDIA also offered their own library for doing this. Some of these tools requires you to relink to their BLAS libraries, or some others only work for dynamically linked BLAS. A lot of restrictions. And more importantly, the performance issue. So as I said, on the conventional GPU architecture, whatever you do with the GPU, you have to copy data from the CPU to GPU, and after calculation, you have to copy the data back. So all these tools have to perform mandatory data copies to and from the GPU for every BLAS calculation. And oftentimes, copy data costs more time than doing compute. And I'm going to show you an example later on when I show you how the auto offload works, how data can be managed in auto offload. So these tools existed for so long, but they have never been really useful in practice unless you just do a simple DGEMM benchmark and not useful at all for real codes. Grasshopper offers that coherent unified memory, so I think that may offer us a new opportunity to rethink how auto offload can work. And I designed this a new tool called Scilab Excel, hopefully not just accelerating BLAS, but also other scientific libraries such as LAPACK and FFTW. And it's really a new tool to overcome all these issues and do performant automatic offload for scientific applications. So how can the tool automatically do offload? And this is a diagram showing how function calls works in your application. So when your application makes a DGEMM call, the execution is the CPU is going to issue a jump instruction that jumps to where the DGEMM function is defined, along with transferring data or putting function arguments in a CPU register. What we wanted to do is we block that path. We hack user binary, redirect the BLAS call instead of to the original CPU BLAS. We redirect it to execute our own BLAS wrapper, say my DGEMM wrapper. And inside the wrapper, we can do data management. As I said earlier, automatic offload really needs a good data management to reduce the transfer overhead. And inside the wrapper, we can do whatever we want. We can call a GPU BLAS, and we can add a timer so that becomes a profiler. And in fact, that's exactly how many profilers are doing symbol interception and doing timing. So how can we do this hacking and redirection? It turns out that is a very mature technique in computer science. And I use a technique that is trampoline-based dynamical binary instrumentation to intercept the symbols. What DBI does, or what trampoline does, is on the right is a piece of simple example of trampoline. This is written in assembly. What it does is there are extra few jump instructions inserted into the function calls and user binary. So when the execution calls a given function called a target function, the jump instruction, extra jump instruction redirects it to our trampoline function. And after we do whatever we want in the trampoline function, we issue another jump instruction, either jump back to the target function or jump back to the original user execution workflow. DBI, as I said, is widely used in profiling. It's a very mature technique. And the beauty of DBI is that it rewrites the binary image in process. So some other instrumentation technique is going to instrument your binary on the disk. That's called a static binary instrumentation. But we do the process on the fly. Nothing the user tells. The binary is hacked when the process loads that binary into the memory. And there's no need for user to recompile their code or relinking. Nothing needed from the user at all. Just loading the DBI binary, DBI library. And this technique is very effective for both dynamically linked and statically linked BLAS. So no matter how you link a BLAS, this tool works. The overhead is going to be negligible because all we do is inserting a few jump instructions. And that's really tiny, very an unnoticeable piece of overhead. And this is because we're replacing a function with another function wrapper that has exactly the same function signature. So if the wrapper function has slightly different function signature, we'd have to back up the function argument in the register, in the CPU register, to the memory stack and restore it later on after we jump back. And that's going to be very expensive. So it's critical to have the target function and the trampoline function having exactly the same interface. But long story short, we have a very mature technique to intercept function symbols and redirect the execution flow for your application. And once that is done, we have to worry about data movement. And data movement is really the most critical thing when you do automatic offload or in general do any GPU programming. So the first data movement strategy is doing CUDA memory copy, and that is very intuitive. Every other tool are doing this. I'm doing it here just to show you how it works and how bad other tools can perform compared to mine. In this strategy, after we intercept the CPU BLAS symbols, it comes to our BLAS wrapper. We do CUDA malloc, allocating the GPU memory. Then we do CUDA mem copy, copying the data, the matrices from the CPU to GPU. Then we pass the GPU pointers to cuBLAS for GPU execution. And in the end, we have to copy the matrix C, that is the result of the modification, back to the CPU. The table in the bottom shows you how much data transfer overhead we can have. So on Grace Hopper, the total runtime is 5.5 milliseconds for doing matrix multiplication of such a dimension. MNK are the input arguments for DGEMM. So your matrix multiplication compute time is only half a millisecond, but your data transfer time is almost 5 milliseconds. So you spend almost all the time just doing data transfer and very, very little time doing the actual compute. It's even worse on the conventional GPU cards. So H100 PCIe version going to spend 32 milliseconds on doing the transfer and just 1 millisecond doing the compute. So the transfer is 7x slower. And this strategy is not effective on traditional GPU architecture and not even useful on Grace Hopper with that high-speed NVLink. NVIDIA offers a library called NVBLAS, and it's supposed to do exactly the same. And turns out that is a very badly implemented software. So on Grace Hopper, NVBLAS is going to take 54.8 milliseconds doing this calculation, but my tool only takes 5.5 milliseconds. On a conventional PCIe card, BLAS somehow also lose 134 milliseconds, where mine only takes 32.8 milliseconds. So something very wrong in NVIDIA's tool. I told them they have not fixed it for a year yet. But anyway, the key here is data transfer is really hurting us, and we needed a good way to manage the data. It's the same data management strategy here, just applied to a real application. So this is a parsec run on almost a 2,000 atoms, 2,000 silicon atom cluster, 2 SCF iterations on Grace CPU. The total runtime is 414 seconds. If I do the automatic offload with CUDA-MEM copy for every BLAS call, it's going to take 425 seconds. Even slightly slower than the CPU version. But the profile is completely different, and that helps us understand better how this works. So on CPU, the total time spent in DGM is 270 seconds. But when you do the automatic offload in CUDA-MEM copy, you only spend 12.4 seconds doing the matrix multiplication, but you spend 220.7 seconds moving around the data. And this just tells again, data reusability is really the key to success. And this is doing frequent copies is the reason that all the existing tools fail to be useful. Another way to manage the data, or second way to manage the data, is through the coherent memory access on Grace Hopper. So as I said, it's a unified memory space. The CPU can access GPU's data, and GPU can access CPU's data as well. And NVIDIA provides a counter on their GPU, measuring how many remote memory access it has, and it's going to actively move data from CPU to GPU. And this thing is going to be very straightforward. You don't have to do any allocation. You just pass your CPU matrix pointer to cuBLAS, and it's going to run. However, this one works extremely bad. NVIDIA has a lot of performance bug in their drivers, in their silicon designs. And when you do such a data management strategy, your total runtime grows to 470 seconds, comparing to just 415 seconds on CPU. And your total DGM, because now we don't explicitly do the data management, data transfer, all the transfer time is embedded into the matrix multiplication time, and spending total 234 seconds on that. So that works really poorly. How can we make automatic offload really work? And how do we avoid frequent data movement? To solve that problem, we have to go back and look at how a matrix, or in general BLAS, are used in real scientific codes. I summarized 3 common use cases. The first one is block matrix multiplication. Here we have matrix A times B equals C, and you can see that for this particular block of A, it's going to be multiplied by every block in the first row of B. So given the matrix dimension is n by n, so every block of A can be reused n times when doing block matrix multiplication, right? In second case, in our world, when doing quantum chemistry or quantum physics, we always do self-consistent field calculation, and that means calculations are performed on the same matrix, exactly the same array pointers over and over again until convergence is reached. So if you just move the data to the GPU in the first cycle of the SCF, let it stay there, it can be reused by all the later cycles, and no extra data movement. And third case is a chain of matrix operations. For example, we have A times B equals C. Then we have some other code accessing C. Then C times D equals E. So C gets reused. And in scientific codes, we don't solve our science problem just by doing one matrix multiplication. We have to do a lot. So this access pattern is also very common. And all of these give us a pretty good chance of reusing the data on the GPU rather than frequently moving it around, right? Make sense? And once you move the data to GPU, then it can be reused by later BLAS calls. And you have to assume that the CPU access of the matrices on the GPU are relatively trivial because after you move the data to GPU, the CPU may want to do some very trivial tasks like tracing a matrix, scale matrix, add a matrix. Those are relatively lightweight comparing doing matrix multiplication. So you leave the matrix multiplication on the GPU, and for this trivial task, you don't move the data back to the CPU. You just let CPU access the data on the GPU through the coherent memory access available on Grace Hopper. And this is the key for this strategy. And if you have done serious OpenMP programming on multi-socket CPU system, and this is going to be sound very familiar to you. It's essentially almost OpenMP first touch. And I call this strategy GPU first use policy. So in the GPU first use policy, we move the matrices to the GPU memory the first time they are used by a BLAS kernel. And those matrices just stays on the GPU throughout its lifetime. And here's a comparison of the OpenMP first touch with GPU first use, and OpenMP first touch exists in almost every OpenMP code. On the left, the picture shows you a simplified dual socket CPU architecture. You have CPU 0 and CPU 1 connected by some interconnect, and you have a memory associated with each socket, each CPU socket. On the right, we have the Grace Hopper architecture. We have CPU and GPU tightly integrated, connected, and each has its own local memory as well. So in multi-socket programming, the issue that people facing and have to use OpenMP first touch is that the CPU accessing, for example, the CPU 0 accessing its own memory 0 is very fast, but it's very slow if you cross the connection and access the memory from the other socket, memory 1. And people do OpenMP first touch so that the data gets localized in the threads, in the socket where the OpenMP thread belongs to. And to compare this to strategies, we can see I laid out 3 most critical features. So for OpenMP first touch, is designed for dual socket CPU, and GPU first use is designed for CPU GPU superchip. And in OpenMP first touch, the memory space is allocated on the local memory of the OpenMP thread upon initialization, while in GPU first use, we migrate the data from the CPU memory to local memory of the GPU upon first access by the GPU kernel. And in OpenMP first touch, we also have to make an assumption that the remote memory access is relatively trivial because you're going to have some cross-socket communication for every code. And for example, CPU 0 accesses CPU 1's memory. And in GPU first touch, we make basically similar assumption. We assume remote memory access is trivial, but the remote memory access is defined slightly differently. It's going to be CPU accessing GPU's memory. And OpenMP first touch is very successful in multi-socket programming. It's simple, easy to use, easy to implement. And I think GPU first use belongs to the same boat. Now we know how we should move our data, but how do we migrate the data from the CPU to GPU? Because when we are in the BLAS call, all those matrices have already been allocated. So, here I have a diagram showing you what happens for a function call. So you have some memories, you have an array gets allocated on the memory, then you'll pass that memory address to your function. So inside your function, you only see these memory addresses. There's no way you can remove them and reallocate them. So how do we migrate data that's already been allocated on the CPU to GPU? To solve that problem, we have to go back to the basics of how memory gets managed in modern operating systems. So all modern operating systems uses a trick called a virtual memory. So here are the addresses we see from the programmer's point of view. They're continuous piece of memory, but all of these are virtual. They have we see continuous address, but physically they might be not. There's no the way it's laid out physically is completely agnostic to programmers seeing the virtual memory, and memories are managed in terms of pages, and that's the smallest unit that the operating system can manage memory. Even if you just ask for 1 byte of data that is allocated on a page, and if you want to move that 1 byte, that entire page needs removed. And operating system or modern processors all have memory management unit that translates the virtual memory space to physical memory space. And on your memory, there's a small piece of space that is reserved to save the page table that basically saves the mapping of virtual to physical memory. And you can see, although we have a continuous memory in our virtual space, physically, the pages can be spread anywhere, and they're not even continuous in this case. And on Grace Hopper, we have the CPU memory or LPDDR5 memory in NUMA 0 or socket 0, and GPU memory in NUMA 1, and they're in a single page table. And this is very similar to dual socket system, the CPU system, as I said many times before. It's possible to move data in a dual socket CPU system, and we can also do that here. And to move the data, there are a couple of steps to do. We have to copy the physical pages from NUMA 0 to NUMA 1. These are the physical memory pages. You can move this page around. And after you move, you have to unmap the original NUMA 0 page, then update the page table so that the memory management unit knows how to translate the virtual memory space to the physical memory space. And all of this process are completely agnostic to the virtual page. So no change to the virtual memory address here at all. And that means your code sees nothing different. All of the things happens underneath in the low level managed by the operating system. Your code, there's nothing affects your code. Your code still uses the same memory pointer, same virtual address, but your physical memory have changed a lot. They have been moved to different places. And turns out this can be done easily by a Linux system called a move page. And move page, if you give it a target and a source, it can move your memory page from NUMA 0 to NUMA 1, basically moving data from CPU to GPU. So our third policy, now we can finally fully implement our third policy, GPU first use policy. Let's just review the salient features. The matrices are moved to the GPU the first time they are used by BLAS, and matrices are going to stay on the GPU memory throughout their lifetime. And this can be implemented by migrating the memory page from NUMA 0 to NUMA 1 using Linux kernel called move page. And the pseudocode here shows you what happens upon intercepting the BLAS calls. We check if that piece of data is on NUMA 0. And if yes, meaning that the data is on the CPU, we call move page to move it to the GPU. And after doing all the data movement, we can call BLAS using just the host pointers, host matrix pointer. There's no new memory allocation. So how does it perform? Originally, we had 415 seconds on the CPU, and by using GPU first touch approach, data management approach, we bring the total runtime down to just 220 seconds. Okay, and DGM time was originally 270 seconds, and now it's just 29.1 seconds. When doing the code memory copy, we spent 220 seconds in data movement, but now using GPU first use, we trimmed that down to just 1.3 seconds. And the critical measure for the usefulness of this method is the data reusability. So for every matrix I move to the GPU using move pages, they get reused by later BLAS calls 570 times. And that's how the data movement time gets reduced from over 200 seconds to just 1 second. So, and this is the very first time that Parsec ever performantly runs on the GPU. The method is universal to many, to all the codes that heavily relies on BLAS. So MUST is another good example. And in fact, MUST works even better than Parsec because LSMS does not depend on scalar pack. For Parsec, there's a major portion of the time spent in scalar pack and the non-DGM portion of the scalar pack. And MAST, I think everybody here is familiar with MAST. It's a suite, and the test case here is the linear scaling DFT. Test case I used is 5,600 atom alloy system. I ran this, collected this profile on 50 grid CPU nodes. There are 5,600 CPU cores used, and you can see here more than 80% of the runtime is spanning BLAS, and this is a profiler that I developed. The two top BLAS functions, ZGEMM and ZTRFM, they spend almost 80% of the total runtime. So it's really a very ideal target for me to apply my automatic offload library. MUST does have a native CUDA implementation using cuSolver, and it turns out automatic offload, it performs 2x better than the native CUDA code. Here I'm showing you the runtime. It's the same test case as I just in a previous slide. 5,600 atom system and running on 50 CPU nodes or 50 GPU nodes. So on CPU, so the runtime is 2,450 seconds, and you spend over 2,100 seconds on these two BLAS routines. We're doing the native CUDA run on the GPU. It does run a bit faster, 1.5x faster than the CPU run, but it's not good enough. When I do the automatic offload with CUDA mem copy, it turns out to be even faster. Even this strategy is faster than the native CUDA code. And we have to spend 340 seconds doing the data movement. The best strategy, the last strategy, is doing the GPU first use, and we trim the total runtime down to just 824 seconds. So 3x comparing to the CPU run using the same number of nodes. And data movement is just 5 seconds comparing to over 300 seconds when you do the data movement in a conventional way. And here, the matrix gets reused 780 times. So for every matrix that I move to the GPU using the first use policy, it gets picked up by later BLAS calls 780 times. And that guarantees that we have good performance for automatic offload. You may notice these two BLAS times are different. They really should be the same because it's all GPU doing calculation on the same data. This is a performance bug. So when I do the CUDA mem copy, data is managed by the GPU's memory management unit and allocated by CUDA malloc. But when I do the automatic offload, what I use is the malloc data on the HBM. Even though on the same memory hardware, just allocated differently. And there's a performance issue that when a GPU kernel accessing malloc, unaligned malloc HBM data is much slower than accessing CUDA malloc data or aligned malloc data. It's a problem reported to NVIDIA about half a year ago, and they have not solved it. And they're too busy selling their GPUs, I guess. So more tests for MUST. This is a large scale run test. I scale MUST from 25 nodes to 200 nodes on Vista. And what I highlighted are the comparison of native GPU code and automatic GPU offload. So the automatic GPU offload turns out to be consistently 2x faster than it could afford. Scalability is awesome, almost close to the ideal scaling. You can see that on the right. And what I wanted to highlight more is the speed up of automatic offload comparing to the CPU ROM. So for a few setups, we achieved more than 3x speed up for the GPU compared to CPU. And this is very important because at TAC or on the machine Vista, we charge one service unit for the Grace Hopper and 1/3 service unit for the Grace CPU node. So the GPUs are essentially 3x more expensive. And by achieving more than 3x speed up doing automatic offload, we're essentially reaching what I called service unit profitability. And we are not only saving runtime, we are also saving cost. And not too many codes in quantum chemistry can do this. Some codes claim 2 to 3x speed up, like Quantum Espresso. So that's a lot being talked about. I haven't tell you how to use the tool. To use the tool, it's extremely simple. You just compile my library and do an LD preload. Then run your CPU code as normal. Then your CPU binary magically take advantages of the GPU. So summary, automatic offload is made performant for the first time. All you need to do is to LD preload my library and run your CPU binary. And just that simple. It's a very easy way to explore GPU capabilities for BLAS heavy codes, such as the codes in quantum chemistry, especially the plane wave codes or real space codes, because those codes tend to have much bigger matrices, where the codes using localized basis set are going to have much smaller matrices, and those matrices sometimes are too small to be to fit the capability of the GPU. The GPUs are too hungry. When matrices are too small, CPU actually runs faster with less overhead. And I think this tool offers a great incentives for people to try out how GPU performs, and later on may get a better idea to fully port your CPU code to GPU. And I think the performance can be further improved once NVIDIA fix several of their performance issues on Grace Hopper. And a quick outlook. So similar technology, similar methodology can be applied to AMD GPUs as well, especially the AMD MS300A APUs, where the CPU and GPUs are packed together with a single piece of HBM memory. And MS300A is available on the EL Capitan machine at Lawrence Livermore National Lab. And on that particular APU, not only BLAS will work well, but also many other math libraries can be automatically offloaded, like LAPACK, FFTW, etc. And I think this is a very promising way to port dozens of legacy quantum chemistry or physics code to GPU with acceptable performance. And many of those codes are very big, has been developed for many decades, and becomes extremely difficult to rewrite in the ported GPU. And using this tool, and user of those softwares may finally be able to move their workflow to GPU. Okay, that's it. I'm ready to take comments or questions.
Okay, thank you, Junjie. It's a great talk. Now let's open for discussion. Any questions? Please go ahead. No question? Let me ask you one question. So on page 22, there's you had my question is like this S1 strategy 1. You with DGM time is only 12.4 seconds, but right. your strategy 3 has like 29.1 seconds. Is that right. Caused by like NVIDIA's bug or just? Ooh.
Yeah, that is NVIDIA's problem. Okay. So overhead is less for mass. The performance difference depends on the size of the matrix and the shape of the matrix. So mass, the overhead not too much. No, it's like 30%, 150 seconds overhead added up to 450 seconds. But for the matrices used in parsec, that overhead is much bigger. And parsecs use a lot of very skinny matrices, long skinny matrices, and those happens to be less optimized by NVIDIA.
Okay, right, thanks. My second question is, so you have provided tool. Does it cover all the BLAS routines only part of it?
So it captures all the level 3 BLASs.
Okay, level 3 BLASs.
Right, because level 3 BLASs has the most biggest ratio of compute versus data movement, which is usually defined as algorithmic intensity. So the higher algorithmic intensity, the more you can benefit from GPU. But for level 1 or level 2 BLAS, it's just a lot of memory movement, but a lot less compute. And moving those routines to GPU is not going to offer as much benefit as the level 3 BLAS.
Okay. Yeah, I guess for users, we don't, we just let it, your tool do that, determine automatically. We don't have to worry about it, I guess.
Right.
Yeah. Okay. Yeah. Another thing is you mentioned not only the ZGen but also ZTRSM, which is a LAPACK routine. So does your library also takes care of LAPACK?
No, this is a level 3 BLAS.
Oh, ZTRSM?
Right, ZTRSM is a level 3 BLAS. No, this is a BLAS. So the LAPACK routine gets used in MOST are ZGE-TRS and ZGE-TRF.
Okay.
And most of the ZGE-TRSM are called from those two LAPACK routines.
Oh, I see. So under this, they use heavily use okay, I see. Okay.
Right. So these are the LAPACK routines you heavily used in ZGE-TRF, right?
Yes.
This is ZGE-TRF, ZGE-TRF.
Oh, I see. Okay. Yeah, I have a wrong impression. I guess I saw the ZTRSM is a LAPACK. Okay, this is a BLAS. Okay. All right. Thanks. Any questions?
May I please ask, out of curiosity, what are the minimal hardware requirements to test this kind of machinery? I mean, you rely on BLAS from NVIDIA as the replaced subroutines. Can you say anything about which generation of NVIDIA hardware would begin giving some support? Not so much for performances, but just to test that things start to work, first of all.
So the best platform to test is NVIDIA Grace Hopper. And that is a very expensive piece of hardware and has very limited availability because Meta and Microsoft bought tons of those, and Attack finally got 560 of these. The other way to test this, I didn't test it, but using the latest Linux kernel, there is a thing called heterogeneous memory management for GPU, or HMM, that essentially simulates this unified memory architecture on a conventional GPU card, PCIe GPU card. So you're going to see unified memory. You're probably also going to see similar NUMA structures, but that's very new. I haven't got a chance to test it. So the most reliable hardware to test this is only the NVIDIA Grace Hopper. In Europe, I know the Switzerland Supercomputing Center in Lugano, they have a few thousand Grace Hopper nodes. And for mass library, of course, we have to rely on the vendor-tuned, optimized BLAS on the GPU and on NVIDIA platform, and we're replacing the CPU BLAS to cuBLAS. And of course, on AMD platform, I'm going to have to replace the CPU BLAS to their ROC BLAS. So that's going to be vendor dependent. So far, I have only written my code on the NVIDIA platform because I don't have access to AMD GPUs.
And in principle, if I understand the strategy, you could use this kind of approach to replace call to one BLAS library to another one, for instance. You could compare against LAPAC, link with LAPAC, but in reality, under the hood, work with the Intel MKL, for instance, all on a CPU, let's say, just.
Right. So one of the things, I actually had an NSF grant for this, is to do a runtime switch of different BLAS implementations on the CPU. Even on Intel platform, MKL is not always the winner. Sometimes for certain operations, matrix in certain shape, open BLAS may win. Or BLAS may be better. So yes, it's possible to do runtime switching between different BLAS libraries and compare their performance. If that answers your question. You can switch. Once you do the interception, you can switch it to anything you like.
Thank you. Well,
any other questions?
Maybe if nobody else has another one, could I ask again a different aspect of your presentation was about these three strategies to, well, basically that scientific codes typically operate on matrices. Yet this slide with three bullet points, you were showing a matrix product, series of iterative operations on the same matrix, and a sequence of matrix operations. I was curious if there was some heuristic in this approach. Do you try to analyze what is the code doing when intercepting its calls, or is there any? I mean, this is a high-level interpretation of what's happening, I guess.
Yeah, this is just a high-level interpretation. I do not analyze the code when I do the symbol interception. In fact, I got inspired by my strategy from OpenMP First Touch. Then I find that strategy works extremely well. And later on, I started to think about why it works so well and how BLAS calls are used in scientific codes. And knowing how BLAS are used is double confirms that the GPU first user approach should work to a broader range of scientific applications.
Okay, if no other questions, I will ask the last one. So what's the plan to maintain this library? So it's going to be you have a teamwork or just only you doing this? Or?
Yeah, it's just me.
Just you, okay. But do you plan to continue to work on it? Or
yeah, I do plan to continue working. Right. I'm going to join AMD next month. Initially, I will be working on the CPU division. Hopefully, later on, I can have some interaction with the GPU team. But yeah, certainly, I'd like to keep maintaining this code and probably migrate it to the AMD MI300A APU, because that's going to work even better than Grace Hopper. And if you look at the actual code, the code is very simple. After I realized I can just use a move page to move the memory pages to GPU, the implementation is very trivial. Just 10 lines of code for implementing the GPU first user approach. It's relatively easy to maintain.
Okay. So I guess to build your library on our local machine is quite straightforward. I would imagine.
Right.
Yeah, okay.
Right. Yeah.
So if you have questions, I can just send an email to you directly.
Yeah, of course. Of course.
Okay. Okay. Thank you very much. I'm going to stop recording and